It's a pleasure, c'est un plaisir d'accueillir Sanjay Ramassamy pour ce séminaire. Donc, c'est un séminaire partagé, physique mathématique et mécanique statistique. Et voilà, donc en fait, Sanjay l'a donné la semaine dernière, mais comme nous, beaucoup de gens n'avaient pas pu l'écouter, on le recommence ici à Saclay. Voilà. Eh ben, écoute, Sanjay, merci, c'est à toi.
Merci pour l'invitation, Vincent et Pierre Francesco. Est-ce que je parle en français ou je le donne en anglais plutôt?
Peut-être en anglais, c'est mieux, excuse-moi. Je fais la présentation en français, mais...
Okay, so I'll switch to English. Thanks for the invitation, Vincent and Pierre Francesco. So today I'm going to speak about some results that are a little bit old, between 2016 and 2018. But recently we have come back to these questions, and we have been working on this again, and I will discuss some newer results towards the end of the talk. So most of what I will talk about is joint work with Bastien Mallein from the Université Paris-13. There will be mainly two models in this talk. The first model is a model of random graphs called Barak-Erdös graphs. They are the directed and acyclic version of the classical Erdös-Rényi random graphs. And the observable we are interested in for these graphs is the length of the longest path. The other class of models we will look at is some interacting particle system called the infinite bin model. It's rather a class of particle systems because every time you consider one probability measure mu on the positive integers, it defines one infinite bin model with moves distributed like mu. And for this interacting particle system, you can imagine you have some cloud of particles drifting to the right. The observable of interest is the speed of the front, the speed at which the cloud is drifting to the right. And in the special case, when you take mu to be the geometric distribution, then there's a coupling between the two models, between the infinite bin model with that mu and the random graphs, Barak-Erdös graphs. And that coupling relates the two observables of interest, the speed of the front of the infinite bin model and the length of the longest path of the Barak-Erdös graphs. So the outline of the talk is that in the first part, I will present to you these Barak-Erdös graphs, and I will quickly show you how they are related to a broader model called last passage percolation. In a second part, I will present to you the infinite bin model, the interacting particle system, and I will explain the coupling between the graphs and the particle system. And in the third part, I will show to you how, from the properties of the infinite bin model that we have derived in part 2, we can deduce properties of the Barak-Erdös graphs. And in part 4, it will be a very short part with some outlooks and perspectives about open questions. And please feel free at any time to interrupt if you have any question, whether on the chat or if you want to switch on your microphone. So first part, Barak-Erdös graphs and their connection to last passage percolation. So how do you construct these Barak-Erdös graphs? You fix an integer n, at least one, and you fix a parameter p between 0 and 1. Then the set of vertices is labeled by the integers 1 to n. So a small maybe disclaimer on terminology. So I will use the mathematical terminology, vertices, edges, graphs. Maybe you are more used to hearing nodes, bonds, and networks, but it will be the same. So the set of vertices is indexed by the integers from 1 to n. And for every pair of vertices, I strictly less than j. With probability p, I add an edge directed from I to j, from the smallest to the largest. And with probability 1 minus p, I don't add any edge. And I do this independently for every pair I strictly less than j. So when I sample my graph, I get something like that. And if I didn't direct the edges, what I would get would be the classical Erdös-Rényi random graph. But here what I get is a graph that is directed and that is acyclic. You don't have any cycles because the edges are always directed from the smallest to the largest vertex. This model was first introduced by Barak and Erdös in 1984. And the most studied observable or feature of this graph has been the length of the longest path. So it's a random variable, Ln of p, which depends on the number of vertices n, and which depends on the parameter p of presence of an edge. So if you have this graph, for example, you have two longest paths, one which starts at 1, goes to 2, then to 4, then to 5, and another one that goes from 1 to 2, to 4, then to 6. And the length is the number of edges in that path, so it's 3 here. And already you see, I say the length of the longest path, but it's a bit an abuse of terminology because there may be multiple longest paths, so I should say the length of a longest path. And this problem has appeared in multiple areas of science. It has appeared, for example, in computer science. If you want to evaluate the time to process a certain number of tasks, where you have infinitely many processes that can process tasks in parallel, but you have some constraints between the tasks. For example, here the vertices, each vertex represents a task, and if there is an arrow from 1 to 2, it means that task 2 needs to be performed after task 1. And if there is no edge between task 3 and task 2, it means that tasks 2 and 3 may be performed in parallel. So if you have some n tasks to perform and you have some random constraints of precedence, that some tasks need to be performed before some others, and you have infinitely many processes to process them, the time that you need to process all the n tasks is the length of the longest path in this graph. You also have applications to mathematical ecology, to food chains. So in that case, each vertex would represent a species. And if you have an edge from I to j, it means that species I eats species j. And you can ask the question, if you have some problem at one end of the food chain, for example, the last species disappears, how long does it take to impact the first species in the food chain? And the answer is, again, the length of the longest path. And there are also applications in applied mathematics to queuing systems. If you want, you can ask me questions about that at the end of the talk. So, as I said, what we are interested in is the random variable Ln of p, the length of the longest path. And Newman showed that this length of the longest path grows linearly as the number of vertices n tends to infinity. And the linear growth rate is denoted by c, and it's a function of the parameter p of presence of a single edge. And what we will be interested in the rest of this talk is the function c of p. So the way I just defined it here is very implicit. There exists a constant c of p, where you can show this using subadditivity. But then it's harder if you want to maybe to find a formula for c of p, but even to prove some properties of the function c of p. So here's a plot of the function c of p. You can see it's increasing, and at p equals 0, it is 0. Why? Because when p equals 0, you don't have any edge in the graph, so the length of the longest path is 0. And when p equals 1, all the edges are present, so the longest path just uses all the edges, 1, 2, 3, etc., until n. And so it is n minus 1, so scales like 1 when you divide by n. So what properties of c of p are known? So there were some that were already known before we moved to this problem with Bastien Mallein. So Newman already proved that c of p is a continuous function of p and increasing, and that the first derivative at 0 is equal to e, exponential of 1. And Foss and Konstantopoulos computed an upper and lower bound for c of p, which are depicted on this picture in blue and yellow. And as you see, these upper and lower bounds are very tight for large values of p, for p close to 1. And so in particular, it gives it gives a Taylor expansion of 5 terms for C of 1 minus Q for Q close to 0. And there already you see that the first 5 terms, they all have integer coefficients. And if you are a combinatorialist like me, you may wonder, can we have the entire expansion, not just 5 terms, but infinitely many terms? And do we always have integers? And if yes, why do we have integers? Do these integers count something interesting in the model? So then we came to this problem with Bastien Mallein in 2016, then again 2018. And the results we proved were the following. First, the function C of P is analytic for P, so P strictly positive up to P equals 1. And we have some formula expressing C of P as the sum of a series. So it is analytic for P strictly positive, but we cannot extend the analyticity up to P equals 0, because at P equals 0, we have a 2-term asymptotic expansion. The first term is EP. We recover the fact that the first derivative at 0 is equal to E, that Newman found. But the second term here is new and is in P over log P squared. And it implies in particular that C of P has no second derivative at P equals 0. So it cannot be analytic up to P equals 0. So that's what we proved for one side, P equals 0. And at the other side, P equals 1, we computed the power series expansion of C of P, and we showed that all the coefficients were indeed integers. So let me now try to put this Barak-Erdös graph model into a slightly larger framework, namely that of last passage percolation. So I will give you some definition of last passage percolation, which is actually not the most general definition, but at least it's some broader framework already. Consider a deterministic graph that is directed and acyclic. For example, this portion, this 2×3 portion of a square grid, where each vertical edge is oriented upwards and each horizontal edge is directed towards the right, and you attach to each edge some IID random length. So here I attach some length, and the length of a path in this graph is the sum of the lengths of each edge length. So here, for example, you have a path of length 10. And the question raised by last passage percolation is to look at the longest path in such a graph and to look at the longest path in the limit when the size of the graph goes to infinity. For example, instead of looking at just a 2×3 portion of the square grid, I would look at a 2n×3n portion of the square grid, and I will ask, how does the length of the longest path scale when n goes to infinity? And actually, one can rephrase the Barak-Erdös graph model in the framework of last passage percolation. How do we do that? The deterministic graph that we consider is the complete graph on n vertices. I represented here a complete graph on 5 vertices. And to each edge, I will attach with probability with probability p, some weight or length equal to 1, and with probability 1 minus p, a length of x. So why do I say weight or length? Because usually when you think of a length, you think of a positive length. But here, 1 is a positive number, the length 1, but x may be positive or may be negative. That's why I say weight, because it's a bit weird to say a path of negative length. And if you take x equals minus infinity, then when you want the longest path or the heaviest path, you cannot use any edge that has weight minus infinity, because already your weight will be minus infinity. You can only use edges of weight 1. So it's the same as saying that you are using only edges that are present in the Barak-Erdös graph. So you recover like this, the Barak-Erdös case. But actually here you have a 1-parameter family generalization of the Barak-Erdös case. And you can denote again by C of Px the linear growth rate of the length of the longest path for this family. So C of P minus infinity is what I called C of P earlier on. And for this model, for this one parameter family, Foss, Konstantopoulos, and Piatkin recently proved a result for C of Px. So here they are fixing the parameter P of presence of an edge, and they are looking at the function where you vary x, and they found that it is non-differentiable exactly for the following values of x. Either x is 0, or x is a negative rational number, or x is a positive integer at least 2, or the inverse of a positive integer at least 2. So this is a recent result on that model. So this is all for the presentation of Barak-Erdös graphs.
Sanjay,
yes,
I have a question. The setting, I see a slight difference between what you present and the usual setting of last passage percolation, for instance, on a square lattice. On the square lattice, you would consider for instance, the last passage time from the bottom left corner to the top right corner. But in your situation and with the Barak-Erdös graph, there could be the situation that that would be the length of the path from 1 to n, but they could be disconnected. So
yes, yeah, it could be. So you can have two definitions: either the length of the longest path from the minimum vertex to the maximal vertex, so like bottom left to top right for Z2, or from 1 to n for complete graphs, or you could have the overall longest path. But it turns out that both have the same scaling, so the limit that you get will be the same.
Okay, thank you.
And feel free if you have other questions to ask, please. All right, so if there is no further question, let me now introduce a completely different model for the moment. It's an interacting particle system called the infinite bin model. So what are the configurations of the infinite bin model? You have infinitely many bins indexed by Z, and each bin might be either empty or contain a finite number of balls, or contain infinitely many balls. For example, bin -1 here with the 3 dots here indicate that there are infinitely many balls in bin number -1. And there is one constraint that I will adopt, is that there is, in such a configuration, a non-empty bin such that every bin to its right is empty. So this bin will be called the front, and the bins to the left of the front may be empty or contain some balls. This is not important. So I will introduce a dynamics on that space of configurations. For every positive integer k, I will define a move of type k. So how do I define a move of type k? For example, a move of type 5. I will count the balls from right to left, starting from the front. So 1, 2, 3, 4, 5. The fifth ball is in bin number 0. So the move of type 5 will add one ball immediately to the right of the bin containing the fifth ball. And in general, a move of type k will add one ball immediately to the right of the bin containing the kth ball. So here it's not important how exactly you count the ball, if this is 1, 2, or 1, 2. It's not relevant. It doesn't change where you will place your new ball. So here is a schematic picture. You start with this configuration, and if you apply a move of type 5, you get this configuration, and you see that in that case, the front didn't move. It's still at position 2. But if, starting from the same configuration, you apply a move of type 1, the first ball is here, so you will add a ball in bin number 3. So if you apply a move of type 1, then you see that your front will advance by 1 unit. So in general, every time you apply some move, either the front does not advance or it advances by 1 unit. So now let me define a stochastic evolution. So I will start from some initial configuration x0, and I give myself a probability distribution mu on the set of positive integers. And I'm going to sample psi n, an IID sequence of integers that are distributed like mu. And I will use this sequence of integers to define my Markov chain. So I start at time 0 with my initial configuration x0, and then from the configuration at time n-1, xn-1, I will apply the move of type psi n to obtain the configuration at time n. So this is a Markov chain that will be denoted by IBM mu, the infinite bin model with move distribution mu. So this model was introduced by Foss and Konstantopoulos in 2003, precisely because they wanted to study the longest paths in Barak-Erdös graphs. But a special case had already appeared in 1983 in work of Erdös and Pittman. It's a special case where you fix some n and you consider mu to be the uniform measure on the integers 1 to n. So what is the observable that we're interested in for this particle system? It's the speed of the front. So we denote by Fn the position of the front at time n. At time 0, it's at position f0. At time n, at position fn. So the displacement of the front between time 0 and time n is Fn minus f0. And this displacement grows linearly with n as n tends to infinity. And the linear growth rate is denoted by v mu. So this linear growth rate depends only on the measure mu and is independent of the starting configuration x0. Foss and Konstantopoulos proved that result in the case when mu has finite expectation, and with Bastien Mallein, we proved it for every measure mu. So v mu is called the speed of the front. Now, what is the relation between this particle system that I just defined and the Barak-Erdös graphs that I introduced in the first part? It's a coupling which is due to Foss and Konstantopoulos. The coupling works only in the special case when you consider mu to be the geometric distribution on positive integers. So I remind you what it is, the geometric distribution of parameter p. You get the integer k with probability p times 1 minus p to the power k minus 1. And in that case, they showed that the speed of the front of the infinite bin model, whose moves are distributed according to a geometric distribution of parameter p, which is denoted by v mu p, this observable for the interacting particle system is equal to the linear growth rate of the length of the longest path for Barak-Erdös graphs that I defined in part 1. So what is exactly this coupling? To explain this coupling, I'm going to grow sequentially my Barak-Erdös graphs, one vertex after the other. The observation is that if you want to sample a Barak-Erdös graph on n plus 1 vertices, you can first sample a Barak-Erdös graph on n vertices, then you add vertex n plus 1, and for each of the previous n vertices, you ask, is there an edge connecting each previous vertex to the new vertex n plus 1? And as I will grow my Barak-Erdös graph one vertex after the other, in parallel, I'm going to run some ball bin process. So my ball bin process will start at time 0 with infinitely many balls in bin minus 1 and no balls in the other bins. And each time I'm going to add one vertex in my graph, I will add one ball in my ball bin process. And where am I going to add my new ball? If I add a new vertex in the graph and the length of the longest path ending at that vertex is denoted by ln, then I will place my new ball in the bin indexed by ln. So this may be a bit abstract, so let me illustrate this on an example. So I grow my Barak-Erdös graph, the first vertex arrives. The length of the longest path ending at that vertex is 0. So I place the corresponding ball in bin number 0. Then the second vertex arrives, and I sample the edges. There is an edge from 1 to 2, for example. So the length of the longest path ending at 2 is 1. So I place the ball associated to vertex number 2 in bin number 1. Then vertex 3 arrives, and it is not connected to the first two vertices. So the length of the longest path ending at 3 equals 0. So I place ball number 3 in bin number 0. vertex number 4 arrives, and the length of the longest path ending at 4 is 2. So I will place the corresponding ball in bin number 2. Vertex 5 arrives, and the length of the longest path ending at 5 is 3. So I place it in bin number 3. And vertex number 6 arrives. And again, the length of the longest path ending at 6 is 3. So I place it here. So this is how the process runs for the graphs and for the ball bin process. And what is clear by construction of the process is that the length of the longest path in the Barak-Erdös graph equals the position of the front in the ball bin process. Now what I need to explain to you is why this ball bin process that I just constructed has the same law as the infinite bin model, with moves distributed like a geometric distribution of parameter p. So let me try to explain what happens if you have constructed already a portion of your graph. For example, you already have 4 vertices in your graph, and the 5th vertex arrives. How are you going to place the 5th ball in your ball bin process? So when the 5th vertex arrives, the first thing you need to look at is, in your graph with 4 vertices, what was the longest path? The longest path here was ending at vertex number 4. So if you have an edge from 4 to 5, then you know for sure that the longest path ending at 5 will be of length 3. You don't need to know if there were vertices between 1 and 5, edges between 1 and 5, 2 and 5, 3 and 5. Just the fact that you know that there is an edge between 4 and 5 would tell you that the length of the longest path ending at 5 equals 3. But if you don't have that edge from 4 to 5, then in order to place vertex number 5, you will need to look at the second longest path in the current graph. So the second longest path ends at 2. So then you would ask the question, is there an edge from 2 to 5? If yes, then already knowing that there is no edge from 4 to 5, you would know that the length of the longest path ending at 5 is equal to 2. So you would place the ball number 5 1 unit to the right of ball number 2. Otherwise, you need to look again at the next longest path. So it was a path of length 0 finishing at 1. If there is an edge from 1 to 5, you will add the ball number 5 1 unit to the right of ball number 1. Otherwise, you go to the next longest path, which is again of length 0, and you would ask, is there an edge from 3 to 5, in which case you would add the ball number 5 1 unit to the right of 3. And if there is absolutely no edge between the 4 vertices and 5, then you add vertex number 5 to bin number 0. So what would an infinite bin model with moves distributed like a geometric distribution do in comparison? It would pick a ball among these 4 balls whose rank follows the geometric distribution of parameter p, and it will add 1 ball immediately to its right. But remember what is a geometric distribution of parameter p. It means that you have some biased coin where you get heads with probability p and tails with probability 1 minus p, and you want to look at the first, you're flipping coins, and you look at the first time when you have heads. And here, so what would the infinite bin model of geometric distribution do? It would first look at the first ball and say, do I add my new ball immediately to its right? Yes, with probability p. No, with probability 1 minus p. Then go to the next ball. Do I add the new ball, immediately to the right of the second ball? Yes, with probability p. No, with probability 1 minus p. And we continue with all 4 balls present. And if we have failures, if we fail for all these balls to add the new ball immediately to the right, we are going to ask the question for the infinite column of balls, and eventually we will have a success and place it in bin number 0. So this is why the 2 processes have the same law. Do you have any questions on this coupling? All right, so if there is no question, let me present some properties of the infinite bin model. So the main tool that we have for the infinite bin model is the construction of a bi-infinite stationary version of the infinite bin model. What does this mean? It means that I initially defined the infinite bin model as a process with time indexed by positive integers. You start with a configuration at time 0, then time flows in the positive direction. But now I want to construct a process with time indexed by z, so positive and negative integers. Morally speaking, what happens is that you have some infinite configuration, some initial configuration at time minus infinity, and you start your process at times minus infinity, and you run it forward. So said like that, it seems that it is not well defined, but there is actually a way to define this rigorously. So what is this way? You give yourself an IID sequence psi n of integers distributed like mu, and you want to construct configurations xn with n again indexed by positive and negative integers, such that you have this recurrence relation. The configuration at times n is obtained from the configuration at time n minus 1 by applying the move psi n. And here psi n is indexed by positive and negative integers. And so the question is, if I give you all the moves from time minus infinity up to time 0, can you reconstruct from this data, can you reconstruct the configuration at time 0? And the answer is yes. We can reconstruct the configuration at time 0 up to a global shift of the front. This was shown by Foss and Konstantopoulos when mu has finite expectation, and by Bastien Mallein and I in the general case. So how do you do something like that? To do that, you go back to the classical infinite bin model, the one that starts at time 0 and goes forward in time. And you say that a word, so a word here is an n tuple of integers, xi1 up to xi(n), is k coupling, where k is some fixed integers, if no matter what your configuration is at time 0, when you apply the moves xi1, xi2 until xi(n), then at time n, the content of the rightmost k non-empty bins is independent of what the configuration at time 0 was. So maybe the position of the front after applying these n moves depends on the configuration at time 0, but the content of the rightmost k non-empty bins is independent of the initial configuration. To give you a very simple example, if I take the word 1, it is one coupling. What does it mean? You take any starting configuration, you apply a move of type 1. So by definition, you have at least one ball in the front bin, and so it will add the new ball one step to its right. So you know that after applying the word 1, in your front bin, you will have exactly one ball. So this word is one coupling. So now you fix k equals 1, and you go back to your infinite word, xi(n), from minus infinity to 0. And the result is that you can go back in time until you find the first suffix, which is k coupling. So for example, from time minus 10 to time 0, you have some finite suffix, which will be k coupling. So the time you have to go back in time to find this first k coupling suffix is almost surely finite. This is the difficult technical result that we had to prove. And once you know it's finite, you just use this suffix to... So this suffix will tell you that no matter what you had before, you apply this word, and it will determine the content of your rightmost k bin. So you define the configuration at time 0 to have this content for its rightmost k bins. And this definition is compatible for different values of k. For example, if you look at the rightmost 3 bins, you construct something, or you could look at the rightmost 5 bins, you would construct something else, but the rightmost 3 bins of the rightmost 5 bins that you constructed are the same as the rightmost 3 bins that you would have constructed if you looked at only 3 bins. So this is how you define this bi-infinite version, and it is stationary. Why is it stationary? Just because the sequence xi(n), which is defined with positive and negative integers, is stationary, invariant under shift. And now that you have this stationary process, the speed of the front is very simple to express. It's just the probability that at time 0, your front advances by 1 unit. And this is some information that you can read off from the sequence psi n of all the moves that you performed in the negative times. So how do you do this? I'm going to define the notion of good word and bad word for the classical infinite bin model started at time 0. So you start at time 0, and you have this word of n letters, and you say that a word is good if no matter what your initial configuration was, when you perform these n moves, at the last step, at step n, the front advances by 1 unit. And you said that this word is bad if no matter what the starting configuration was, when you apply the word, at the last step, the front will not advance. So let me show you this on 3 examples. So at the bottom here, I have 2 possible starting configurations, and I will apply to them first the word 1. So I will apply the word 1 to the first configuration. You see that the front advances at the last step. For the second configuration, I apply the word 1. Again, you see that the front advances at the last step. And you can show that it is true for any starting configuration, so the word 1 is good. Now, if I start from this left configuration and I apply the word 2, 3, so I first apply a move of type 2, so I have this ball, then a move of type 3, I have this ball. You see that at the last move, the move of type 3, the front did not advance at the last step. Now, if I start from this right initial configuration and I apply a move of type 2, then a move of type 3, at the last step, the front did not advance either. And you can show that no matter what the starting configuration is, if you apply the word 2, 3, at the last step, the front will not advance. So the word 2, 3 is bad. And then I'm going to look at the word with 1 letter, which is 2. Starting from the left configuration, if I apply a move of type 2, the front advances by 1 unit. And starting from the right configuration, if I apply a move of type 2, the front does not advance at the last step. So it means that the word 2 is neither good nor bad. So you have 3 categories of words. You have good words, bad words, and words that are neither good nor bad. So what do you do if you want to compute the speed of the front for the infinite bin model? You look, so you want to know if the front advances at time 0. So you need to look at your infinite word of integers between -infinity and 0. And starting from 0, you go back in time until you find the first suffix, which is either good or bad. And the result is that this will happen almost surely in finite time. And then the speed of the front is just the probability that the suffix that you just cut is good. So this allows us to have some formula for the speed of the front of the infinite bin model. As you may observe, you will cut your infinite word the first time that you find a good or a bad word. Since you are taking the first time, it means that if you find a good word, it will have the property that no strict suffix of this good word may be good. Otherwise, you would have stopped before when you went back in time. So I denote by GM the set of good words that have no good strict suffix. For example, 1 is a good word, and it is also good minimal. GM means good minimal. But 1, 1 is a good word, but it's not good minimal because it has a strict suffix, which is just 1, which is good. And then given a word alpha, I define the weight of alpha to be just the product of the probabilities on the mu of each letter. So for example, the weight of the word 2, 1, 3 is probability of 2 times probability of 1 times probability of 3. And the formula, the series formula that we have with Bastien is that for any infinite bin model, for any mu, except the trivial case of when mu is a Dirac mass, in which case the model is deterministic, then we can express the speed of the front v mu as the sum of the weights of all the minimal good words. So 2 things about this formula. It is nice enough that we can prove the properties that we want, particularly about C of P. using this formula, but it is not very explicit in the sense that there is no simple characterization of the set of minimal good words. So we would still like something maybe a bit more explicit. It would be nicer. And one maybe more applied remark about this this bi-infinite stationary process, it is that it enables perfect simulation of the model. So what is perfect simulation of a Markov chain? We are more used to MCMC methods, Markov chain Monte Carlo methods, but these methods sample according to a distribution which converges to the stationary distribution. So when you sample, you will stop at a time when you have some distribution which is close, very close to the stationary distribution, but not exactly equal to the stationary distribution. And perfect simulation is when you can sample exactly from the stationary distribution of a Markov process. So it's stronger than MCMC methods. And in this case, because we have this bi-infinite stationary process that we can construct in almost infinite time by going back in time, finite time, this makes it possible for us to simulate perfectly any finite dimensional marginal of the infinite bin model. For example, if you want to know the content of the rightmost k bins for fixed k at stationarity, this is doable. So it was first shown by Foss and Konstantopoulos for mu with finite expectation, and then by Bastien I in the general case. And I mentioned in the introduction that there was some one-parameter family generalization of Barak-Erdös graphs that were last passage percolation on complete graphs with two weights, 1 and x. We can associate to this some particle system, and it's work in progress with Foss, Konstantopoulos, and Bastien Mallein to define a perfect simulation algorithm for such particle systems. So this is the end of the presentation for the properties of the infinite bin model. Let me know if you have any questions, and then I may explain to you how to use these properties to prove properties of Barak-Erdös graphs.
So I have a question. So is there an algorithmic way in which you can decide whether a word is good or bad?
There are some classes of words that are easy to check. It's triangular words. So a word is triangular if the first letter is equal to 1, the second letter is 1 or 2, the third letter 1, 2, or 3, and so on. In that case, you can start from any initial configuration and you just run the word and you look at what happens at the last step. So there's just one initial configuration against which you need to test. But if you have an arbitrary word, which is not triangular, then it is harder, and you need to look at more or less the largest letter in the word. For example, if it's 10, then you need to test against a number of configuration that is exponential in the value of the largest letter in the word. So it is quite cumbersome in general. Okay, so if there is no further question, let me explain to you how to get the properties of C of P that I explained in part 1 from these properties of the infinite bin model. So I just show you a formula for the speed of the infinite bin model for general mu. We can specialize it to the case of the geometric distribution of parameter P. And in that case, you know, because there is a very simple formula for the probability of an integer k under the geometric distribution, this gives us some formula for C of P. C of P is the sum over minimal good words of P to some power times 1 minus P to some power. So what is the exponent of P? The exponent of P is the length of the word alpha. So if you have the word alpha, which has letters alpha 1 to alpha n, the length is just n. And the exponent of 1 minus P is what we call the height, h of alpha. And the height of a word is the sum of the letters in the word minus the length. And once we have this formula, to prove that C of P is analytic for P strictly positive, all we have to do is to prove that when we had the infinite bin model, the stationary version, the time that we have to go back in time, starting from time 0 and going into the negatives, until we find a good word or a bad word, that this waiting time has finite exponential moments. The existence of these finite exponential moments implies the analyticity of C of P for P strictly positive. Now, what happens for dense graphs when, when P is close to 1? We rewrite Q equals 1 minus P, and we look at C of 1 minus Q when Q is close to 0. Then we can, using this formula, sum over minimal good words, we we truncate up to some maximal height, and the rest will be a little o of Q to that height. And we get, by expanding using the binomial formula, we get only integer coefficients. So we have that indeed the first 5 terms that Foss and Konstantopoulos found were integers, but that in reality, all the terms in the power series expansion around Q equals 1 are integers. And with Bastien, we found a lower bound of at least root 2 minus 1 over 2, which is at approximately 0.2 for that radius of convergence, but it is not expected to be optimal. My master student, Benjamin Terla, recently found a proof, I think, saying that the radius of convergence was at least 3 minus root 5 over 2, which is approximately 0.4, which is better than our bound. But I still don't expect this to be optimal, because if you look at the coefficients, eventually the an plus 1 over an is less than 1/2. So I expect the radius of convergence to be less than 2. So I expect the radius of convergence to be at least 1/2, but probably strictly less than 1. So this is what happens for dense graphs and the limit when P is close to 1. On the other side, when P goes to 0, then we showed with Bastien that we have a 2-term asymptotic expansion, and the second term is in P over log P squared, implying that you have no second derivative at P equals 0. So how do you get that from the infinite bin model? So what we are starting from is the infinite bin model with move distributed like mu P, where mu P is a geometric distribution with parameter P, which is very small. So the first thing we do is to compare this to an infinite bin model where you have move distributed like mu, which is the uniform distribution on some integers 1 to n, with n very large. And now you forget about the infinite bin model mu P, you just have the infinite bin model with uniform distribution on some set of integers 1 to n with large n. And this infinite bin model with uniform distribution, you can couple this with a model called branching random walk with selection. And then you use the vast literature on branching random walks with selections. You have many estimates known to derive some estimates for the model that we are interested in. So to give briefly a sketch of each step. So as I said, first, you start with the infinite bin model with geometric distribution mu P, with parameter P small. And if you say that P is 1 over n with n very large, then the probability of 1 is 1 over n. The probability of 2 is very close to 1 over n. Same for 3 up to, say, up to move 10 maybe. And afterwards, the probabilities are a bit different between the uniform distribution and the geometric distribution. But if you have 2 infinite bin models with 2 different mu's, but such that the probabilities of the small moves are very close, then the speeds of these 2 infinite bin models will be very close. So because the probabilities of the small moves are very close for geometric of 1 over n and uniform over 1n, we can approximate the speed of the infinite bin model mu P by the speed of the infinite bin model with uniform distribution on the integers 1 to n. We call that the infinite bin model nu n. And this infinite bin model, nu n, first appeared in work of Erdös and Pitman. And this can be coupled to a process called continuous time branch-chain random walk on Z with selection of the rightmost n individuals. So what is this? So you have n particles, here n equals 6 on the picture, and each of the n particles carries an exponential clock, independent exponential clock of parameter 1. And whenever the first clock rings, for example, the clock of this particle that is circled, then it will produce a child particle one step to its right. So now you will have n plus 1 individuals in your system. So you will need to apply the selection part. So the selection of the rightmost n individuals means that you will kill the leftmost individual to come back to n individuals. So in general, branch-chain random walks, so it's more general because you can have a random number of children for each parent. Here it's deterministic, it's one child. And the position of the children around the parent may also be random. Whereas here, it's a very special case where the position of the child is deterministic around the parent. And now that we have this, so we have continuous time branch-chain random walk with selections, there is a vast literature for discrete time branch-chain random walk with selection. We need to translate the discrete time results to continuous time results, and we can apply it to our problem. And Brunet and Derrida have a conjecture for the next term for discrete time branch-chain random walks with selection. And if that conjecture of Brunet and Derrida is correct, then we would get the third term in our asymptotic expansion for C of P, for P close to 0, which would be in P log P over log P cubed. All right, so this was the explanation of how we got the results for C of P. Now, let me move to the last part, which is about some further problems. So one thing which I find very interesting is what happens around P equals 1. So P equals 1, I write Q equals 1 minus P. So I can write the expansion C of 1 minus Q as this expansion. As you see already on the first terms, that the signs seem to be alternating between positive and negative. So I'm going to rewrite this expansion as the sum of minus 1 to the power k to account for alternating sign times ak to q to the power k. And what we know with Bastien, the only thing we know, we prove, is that ak is integer. We don't know that ak is a positive integer, and we don't know that it grows. So it is a constant here at the beginning, 1, 1, 1, but after that it will be strictly increasing. The first 5 terms were found by Foss and Konstantopoulos. With Bastien, we had some method to find up to 17 terms. And recently, my master's student, Benjamin Terla, has developed some methods allowing him to find already 24 terms. So you may wonder, why would one want in practice to know many terms of the sequence? Maybe it sounds a bit vain, you know, we already have 17 terms, why go to 24, why go to further even? But I will explain to you in maybe 2 slides why we are interested in having, as many terms as possible for that sequence. So one reflex when you see a sequence of integers is to go to the online encyclopedia of integer sequences and check whether the sequence is present in there or not. And it was not present in there in 2016 until I added the sequence. So now if you look it up, you will find it under the number sequence A 321309. And so open question, show that AK forms an increasing sequence of positive integers. And when you're a combinatorialist and you see like this a generating function for some integer sequence of positive integers, you suspect that there may be some class of some nice class of combinatorial objects counted by these integers. So find such a class of combinatorial objects counted by these integers. another question is, so all the proofs that we have for the Barak-Erdös graph for C of P use the infinite bin model. Can we find proofs that use only the graphs and not the infinite bin model? And actually, this may be a bit related to the previous questions, because maybe the class of combinatorial objects counted by the integer sequence may be some class of graphs. We have some idea with that with some people of what kind of graphs maybe could be counted by this sequence. And then the dream would be, C of P was defined very implicitly. We managed to find some properties, some expansions, but can we have some sort of explicit formula for C of P? So what kind of explicit formula could we expect for C of P? Let me just give you some typology. So when you have an integer sequence or just a sequence, you can write UK, you can write the generating function of UK as f of q equals sum of UK q to the power k. And there are several nice classes of generating functions and combinatorics. You have rational functions. It means that f of q is the quotient of two polynomials in Q. You have algebraic functions. It means that there is some polynomial in two variables, such that when you evaluate this polynomial in the variable Q and in the variable f of Q, you get 0. So f of Q is the solution of a polynomial equation whose coefficients are polynomial in Q. Then you could have that f of Q is solution of some differential equation. If f of Q is solution of a differential equation which is linear in the function and its derivatives, and the coefficients are polynomial in Q, this is called a d-finite function. And if the differential equation is nonlinear in the function, for example, you can have a f squared or f times f prime in your differential equation, then this is called d-algebraic. And these classes are included one inside the other. If you are rational, then you are algebraic. If you are algebraic, then you are d-finite. If you are d-finite, then you are d-algebraic. And we have a negative result already because of the singularity of the function C of P at p equals 0. We know that the function cannot be rational, cannot be algebraic, and cannot be d-finite. So in the typology that I gave you on the previous slide, the only possibility that would remain for a nice class of function for C of P would be d-algebraic. So it would be nice if we could have that C of P is d-algebraic, and if we could find explicitly the nonlinear differential equation satisfied by C of P. So here comes the knowledge of the first few terms. So there's a maple package called gfun for generating function, developed by Bruno Salvi. And if you feed in enough terms of the sequence UK, then this package can guess the generating function if the generating function falls in one of the previous 4 categories, in particular if it is d-algebraic. And I asked Bruno Salvi how many terms maybe do we need for C of P for this function to guess the differential equation. He told me maybe around 40 terms could do. So with 17 terms, it didn't guess the equation if there exists such a differential equation. That's why we want to get more terms, to get maybe 40 terms, in order for this guessing package to give us maybe the answer. And that's all for me. Thank you for your attention.
Thank you, Sanjay. That's great. So maybe there are questions now.
May I? Hi, Sanjay.
Hi, Kiran.
It's Kiran, yeah. Very, very nice talk. I had a very simple, probably elementary question. When you were talking about the CPX, you said that it was not differentiable for x integer negative or 1 over integer negative. Is there a simple argument related to degeneracy or something like that? That you have a finite degeneracy with probability non-zero that explains that?
So the reason for that is the following, is that so you have the complete graph, and you are assigning to each edge of the complete graph either weight 1 or x. And when x is one of these values, negative, rational, or whatever, then there exists some complete graphs and some assignment of edge weights, 1 or x, to these edges, such that there are two maximal paths, two paths of maximal weight in that graph, but these two paths have a different number of edges of weight x.
Yeah.
So basically, this is the...
Yeah, so it's indeed related to some degeneracy.
Yes.
Yeah, okay. Yeah, thank you. Because something similar happened, I encountered that once, when one counts in permutations, the length of the biggest permutation. If you have a permutation and the length of the biggest cycle, you have also this kind of singularities in the distribution of the length of the biggest cycle when it is a finite fraction of the total length because of degeneracies. So yeah, okay. Merci beaucoup.
So may I ask another question? Why do you expect that the radius of convergence is less than 1 for when you expand C of P close to at P equal 1?
So sorry, my printer is making some noise. So you can plot the graph of the Taylor polynomials. So you take your 17 terms that we knew with Bastien, and you truncate, and you get 17 polynomials. And when you plot them, you see that they will tend to plus infinity, maybe around 1 point. You need to extend beyond P equals 1, around maybe 1.56. I mean, somewhere between 1.5 and 1.6. So I would expect that if you continue analytically the function beyond P equals 1, then you would tend to plus infinity before you get to P equals 2.
The question, did you try, there are some methods used by Gutmann and other people to accelerate convergence of these estimates. So did you use these methods?
Accelerate the convergence of what?
Okay, but that's okay. We can discuss that later.
Okay.
But I had another question. So about the fact that you can rule out algebraicity of C of P based on the expansion as at P equals 0, but wouldn't that argument be only true when this singularity is still within the radius of this convergence? Because I mean, if imagine you could have a C of P which is algebraic, but this equality only is valid in a finite range, and then you jump to something else which has this weird singularity. But
well, the function is analytic. So if it is algebraic, it should be algebraic everywhere, even outside the radius of convergence.
Ah, okay, because it's
analytic.
No, it's analytic for every P between 0 and 1.
Yes.
Okay, I see. Okay, thank you.
I have a question.
Mm-hmm.
Could you show please formula for C of P for small p?
What formula, sorry?
You had a formula for C of P for small p. It was term linear in P, and then there was something over log P.
This one?
Yeah, this one. So this formula has some interesting feature, which actually comes from a different branch of mathematical physics. So if you're looking for how space organized, so the first correction has a property of having certain weight. What I mean by this is that some time ago people were playing the game. So imagine I will associate with pi some weight 1 and with log weight 1. Then you see that the second term has pi and log in such combinations that total weight is 0. So if I continue further, let's say if I were to guess how the expansion would look like, so if I take it like as a guiding principle, then I would say that the correction, yes, the correction should have the same property propagated to higher terms. And what you see here, you have pi square, which weight 2, log weight 1 divided by log power 3. So it's again weight 0, which tells me that if I continue further, I could come up with certain ansatz. And that's basically would be the one where if you accept the expansion rules only powers of pi's, then you have to have a balance between powers of pi and powers of logs. But what I know from another example that at some point you may have other numbers entering like zeta of 3. Is it feasible? I mean, could you imagine something like this happening, that other numbers, zeta functions appearing in the expansion?
This I don't know, because this is basically I don't know the details of the proofs for the branching random walks. You know, we just took the result. I mean, Bastien is a specialist of that, but we just took the result and translated it. So to know whether you would have this zeta of 3, you would need to look in the. You could have this. You would need to look in the branching random walk literature, and this I don't know.
And another kind of crazy question that similar formula. Okay, I've seen similar formula appearing in different business when you're dealing with, for example, some elliptic curve. Could imagine existing some relation? For example, such kind of law could appear, for example, thinking about some kind of elliptic curve and then looking for the point when one of these periods shrinks to 0. Then one of the periods will necessarily develop singularity. And well, the crazy question is there any remote relation between these asymptotics for p equal to 0 and to p equal to 1 to expansion sort of function defined, let's say, in some elliptic curves? And once again, these two limits that you're talking about, the limits corresponding to the degeneracy of the elliptic curves.
Why would p equals 1 correspond to degeneracy also?
Because normally, if you think like you just have a torus, so you have two periods on the torus, and then there is one limit in one period goes to 0, and then a second limit when second period goes to 0. Normally, what happens in one of these limits, one of the periods will be staying regular. It will have very nice analytical expansion around the singularity point, and another will necessarily have some logarithmic singularities.
I see.
And what I'm saying is that if I look for your two expansions, one expansion is perfectly regular around that point, another has singularities. And normally, and moreover, if I were to guess, let's say you have the expansion which involves integer powers, which looks very much on the expansion of would be eta function. So if I have the elliptic curve, I could easily write some eta function expanding over periods of this curve, and then the expansion of eta function will be exactly expansion which involves only integer numbers. I'm not saying they're exactly the same numbers which you have got, but I'm saying there is some analogy which may have nothing to do with what you're talking about, but I'm simply just drawing the analogy.
I see. Well, maybe there is some deeper structure in there, but we would need to find it somewhere. I don't know where to find this elliptic curve, where it would come from.
But you said how many numbers do you have in the expansion? I say well, p equal to 1.
So far we have 24.
And there is no any regularity, there is no simple guess you could make about how these numbers looks like analytically?
No, and they are quite complicated because since the generating function cannot be rational, algebraic, or definite, it means that you have no simple recurrence relation between these numbers. It has to be quite complicated somehow because of this.
Thank you.
Well, thanks for the comment. It was very interesting. Maybe we can talk about that.
Okay. Well, if there is no more question, thank you very much, Sanjay, for this interesting seminar, and